Okay, this is section 17.3, acid-base titrations. Now we're going to look at a titration that has a weak acid with a strong base. In part one, we looked at a strong acid with a strong base. Now we're going to do a weak acid with a strong base. And we're going to look at 4 different points. So the strong acid is sodium hydroxide, NaOH. Sodium hydroxide in this problem will have a concentration of 0.100 moles per liter. It's in the burette. It will be added into a solution of acetic acid. Acetic acid is a weak acid with a Ka of 1.8 times 10 to the minus 5. And we're going to use 25 milliliters of the acetic acid solution. And it will also have a concentration of 0.1 molar. So the first volume addition is 0, so we're not going to add any sodium hydroxide to begin with. So that means we're going to determine the pH of just the acetic acid solution. So how do we do that? It's a weak acid, so this is a weak acid problem. So a weak acid problem, the weak acid reacts with water to form hydronium and the conjugate base. Okay, the initial concentration of acetic acid is 0.100. Water is a liquid. The initial concentrations of the products are 0. Q is 0 because the concentrations of the products are 0, which means that Q is less than K, so the reaction will proceed to the right. Plus X on the product side. And at equilibrium, we have 0.100 minus X for the acetic acid, and then X for each of the products. So Ka is the concentration of the products, so that's X squared, divided by 0.100 minus X, and that is equal to 1.8 times 10 to the minus 5, which is a relatively small number. So we can simplify this to X squared over 0.100. That should be equal to 1.8 times 10 to the minus 5. X squared should be 1.8 times 10 to the minus 5, just algebraically going through it, times 0.100, which is 1.8 times 10 to the minus 6. X would be the square root of that. So square root of 1.8 times 10 to the minus 6. Okay, square root of that. 1.34 times 10 to the minus 3. Okay, so the pH would be minus log of that. .87. So there's your pH, 2.87. Okay, weak acid, pH of 2.87. Keep in mind that had it been a strong acid, the pH would have been 1.00. A strong acid, yes. Now we're ready to do the second part, which is we're going to add 10 milliliters of sodium hydroxide solution to this weak acid solution. So our volume is going to go up to 35 milliliters. And now it's a reaction. The reaction is we're adding sodium hydroxide to acetic acid. So I'll write the acetic acid first. And then the sodium hydroxide. Okay. Strong base, so the reaction goes only in the forward direction. If one or both of the reactants are strong acid or strong base, the reaction goes to completion. Okay, products, switch partners. The conjugate base is the acetate ion. That's going to combine with the sodium. The hydrogen ion is going to combine with the hydroxide. So water plus sodium acetate. Okay. Now, just as in the previous problem, it's very useful to use millimoles. So let's do the millimoles calculation. Concentration is 0.1 molar. Volume is 25. Molarity times volume is moles. If the volume is in milliliters, you'll get millimoles. So 2.50 millimoles of acetic acid. Do the same thing for the sodium hydroxide. Concentration of sodium hydroxide is 0.100 moles per liter. The volume is 10 milliliters. So that's 1 millimole. Looking good so far. Water's a liquid, you don't need to worry about that. This one right here initially is 0. Now the limiting reactant is the sodium hydroxide. 1 millimole is less than 2.5 millimoles. So that will limit how much of the reactants can react. So we subtract 1.00 from both of the reactants. And now I'm going to actually go ahead and gain 1 millimole of the product. Not water, but the sodium acetate. And so at equilibrium, not at equilibrium, at the end, after the reaction is done, we'll have a millimole. Okay. Now, the mixture that we have in here is sodium acetate, which contains the acetate ion, and acetic acid, which is a weak acid. So look at what you have in this mixture. We have a weak acid, and we also have its conjugate base. So we ask ourselves, is there anything special about a solution that has a weak acid and a conjugate base, its conjugate base? And if you recall the discussion of buffers, a buffer is a solution that has a weak acid and its conjugate base present at the same time. So this is, lo and behold, a buffer solution. And we said that if we wanted to calculate the pH of a buffer, we would use the Henderson-Hasselbalch equation, where the pH is equal to the pKa plus the log of the ratio of the concentration of the conjugate base. Now, sodium is not part of the conjugate base, but the product is sodium acetate, so we'll go ahead and write the whole formula in there, divided by the concentration of the weak acid. How about that? So if we can figure out those three values, we'll have the pH. Okay? So anytime you do an acid-base titration and one of the substances is a weak acid or weak base, you will often have a situation where in the titration calculations you have a buffer solution. So as long as you have some of the conjugate base and some of the weak acid, you have a buffer there. So anywhere in between above 0 and up to the equivalence point, it would act as a buffer. Okay? So the pKa of acetic acid is the negative log of the Ka. Covered that earlier in the previous section. That's the negative log of 1.8 times 10 to the minus 5, and that's 4.74. Plus the log of the concentrations. Now, we can go ahead and calculate the concentrations if we wanted to, But keep in mind, concentration is the number of moles, in this case millimoles, divided by the total volume in milliliters. And that's true for both of them. Millimoles of the acid divided by the volume in milliliters. So it's the total volume. These two cancel. So really all you need to know are the millimoles, and that'll give you the ratio right there. So the number of millimoles of the conjugate base is 1, and the number of millimoles of the weak acid is 1.5. That's a nifty little simplification. So 1 over 1.5 is 2/3, 0.667. So all we need is the log of 0.667, add that to 4.74, and you got your answer. So let's come back over here. 0.667, we'll take the log of that, not negative log, but log, because it's plus the ratio, not p. So add that to 4.74, and you got 4.56. So there's our pH. Take a look at what happened. It went all the way up to 4.56. Okay. pH is 4.56 after we've added 10 milliliters of the base. Now the next calculation I'm going to go ahead and erase all of this here so that we have room to work. And I'll rewrite the equation, the chemical equation. We're now doing 25 ml. So acetic acid, again, is going to react with sodium hydroxide to form water and sodium acetate. Okay, we knew this was 2.5 millimoles. This was 0. And now it's 25 milliliters of sodium hydroxide, and the concentration is 0.1 molar. So 25 times 0.1 is 2.5. So it's 2.5 millimoles. Now notice we're now at the equivalence point. Remember from the previous titration that we looked at in part 1, if the number of millimoles are equal of both reactants, that's called the equivalence point. So what happens is we subtract the number of millimoles for each, but they're equal. And so you get 0 for both the reactants, but we do now have 2.5 millimoles of the conjugate base. So this is going to be a basic solution because this is a weak base. So at the equivalence point, this will be above pH 7. We just have to figure out what the pH of this weak base is. So this becomes a weak base problem. Now, calculating the pH of a weak base requires that we know the Kb, right? So the question then is, if Ka is 1.8 times 10 to the minus 5 for acetic acid, what is Kb for the acetate ion? Oops, let's write that whole chemical formula there. Right, this is the conjugate base of acetic acid. You just take the H plus off. Well, the Kb is Kw over Ka. So that would be 1.0 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. Now, if you run that through your calculator, you'll find that it's 5.56 times 10 to the minus 10. It's pretty small. It's a very weak base. The acetic acid is a weak acid, but its conjugate base, the acetate ion, is a very weak base. 10 to the minus 10 is the Kb. So we're going to write the reaction then for that process. How do we calculate the pH of a weak base? You may notice that this titration is running us through all the different types of things that we learned to do back in Chapter 16. It's very important information in Chapter 16 for these types of problems. So here's how we'll do it. It's a weak base. Weak bases react with water. The H plus goes from the water to the base. So now you get acetic acid and you get hydroxide, right? That's the mechanism of weak bases forming basic solution. They react with water, take a hydrogen ion off of the water to form a weak conjugate acid and the hydroxide ion. And now we know the Kb value for that weak acid is weak base is 5.6 times 10 to the minus 10. Now the question then is, well, what is the concentration of this acetate ion? We have to calculate that too. So let's see if we can figure that out. The volume is 25 milliliters plus another 25 milliliters. So that's a 50 milliliter volume. The number of millimoles that were formed was 2.5 millimoles. So that means that the concentration of acetate, the initial concentration, would be 2.50 millimoles divided by 50 milliliters. Okay, so that's 0.05 molar. Right, the millis will cancel, it's moles per liter, so that's molarity. 25 over 50 would be 0.5, so 2.5 over 50 would be 0.05. So 0.050 molar. Again, this is a liquid, we don't need to worry about that. These are initially 0. Q is 0, so the products are formed from the reactants. And so then at equilibrium, 0.050 minus X, X and X. Very small X, because if you look at that Kb, it's tiny, so we're going to have a very small amount of X. So that means that we can make a nice little assumption, simplify the algebra in terms of finding X. Okay, so we have Kb equals X squared over 0.050 minus X. And that is equal to 5.6 times 10 to the negative 10. Okay, well, again, we're going to simplify that. So we've got X squared over 0.05 is equal to 5.6 times 10 to the minus 10, which means that X is the square root. I'm just going to go ahead and cut to the chase here. The 0.050 times 5.6 times 10 to the minus 10, right? You multiply the denominator by the value of Kb and then take the square root. So let's figure out what that is. 0.050 times 5.6 times 10 to the minus 10. There we go. Now we're going to take the square root of that. 5.29 times 10 to the minus 6. Now that X, for our purposes, what's important is that that's the concentration of the hydroxide. That means that we can calculate the pOH as the negative log of 5.29 times 10 to the minus 6. Negative log, so log negative 5.28. And then remember, that's not the pH, that's the pOH. So pOH is 14 minus pOH, or 5.28. So 14.00 minus 5.28, and you get 8.72. So it is basic at the equivalence point. Now that's significant for us because in the previous titration, the one we looked at with a strong acid and a strong base, the equivalence point occurred at a pH value of 7, neutral. That is not true if you have a strong base with a weak acid. So if the base is strong but the acid is weak, the equivalence point will occur in the basic region. It'll be a basic, because the base is more powerful chemically than the acid is, because it's strong versus weak. If they're equal strength, meaning strong acid, strong base, then they'll be neutral. It'll be pH 7. Okay? So we got one more point to do, which is the 35 ml. I'm going to actually leave our equilibrium equation here. Actually, you know what? Let me go ahead and erase that as well. 35 ml. So we know that we had 2.50 millimoles of acetic acid. How many millimoles of sodium hydroxide are we adding if we add 35 now? It'd be 35 milliliters times 0.1 moles per liter, so that would be 3.5 millimoles. Okay, so let's write the reaction. Acetic acid plus sodium hydroxide. Again, one of them strong, so we write this as a one direction. And you get sodium acetate and water. (2.5 millimoles), 3.5 millimoles. Actually, unimportant, and then I'll make that 0. So subtract 2.5, subtract 2.5, add 2.5, water is important, 0, 1.0, and 2.5. So now, just sort of looking at what you have a weak base with 2.5 millimoles, and you got a strong base with 1 millimole. So this could, in theory, be a pretty complicated problem. You'd have to figure out how much hydroxide comes from the sodium hydroxide. Well, that's not hard. But you'd also have to figure out how much hydroxide comes from the acetate, because that's a weak base and it forms acetate, it forms hydroxide as well. And then add the two together. But luckily for us, when you have a weak base and you combine it with a strong base, the pH is dominated by the strong base. So you can ignore the effect of the weak base. And you only need to worry about the strong base. So that simplifies things. We could show that through calculation, but it would take another 10 minutes or so. So that means we've got a strong base problem. Okay, well, we have 1 millimole of sodium hydroxide. What's the total volume? The total volume is 35 ml plus another 25 ml, so that's 60 milliliters. That's the volume of the solution. So that should be 0.0167, but let's check it. 1 millimole divided by 60 milliliters, 0.0167. Okay, so that means that we can find the pOH pretty easily. Negative log of 0.0167. Log negative 1.78. pH would be 14 minus that. 12.22. So we got our last value here. Okay, so there you go. 4 separate calculations. I wanted to show all 4. The before the titration begins, prior to adding, but prior to the equivalence point. The equivalence point, which in this problem is 25 ml, and then post equivalence point. just as with the strong acid, strong base titration, we definitely want to take a look at a curve. Oops, let's do this piecemeal. Okay, so here's what we're going to do. We're going to have 4 pH values, so volume, this is the volume of the base added in milliliters, and then pH. 2.87. So this was when we didn't add any. When we added 10, we had 4.56. When we added 25, we were at 8.72. And then when we added 35, we were up at 12.22. So let's draw a curve. Again, the titration curves are shown in the following way. The titrant is the substance in the burette. It's being added. So the volume of the titrant is shown on the x-axis. In this particular experiment, it's done in milliliters. pH is shown on the x-axis, on the y-axis, sorry. Okay, increasing pH in this direction. And our pH values started at a little under 3 and went up a little bit over 12. So let's do this. Let's do 2, 4, 6, 8, 10, 12, 14. And then volume added, we went up to 35, so let's do this. 10, 20, 30, 40. Okay? So when we didn't add any, the pH was 2.87, so that's a little under 3, so that's right there. Then we added 10 milliliters and it went up to 4.56. So 10 went up to a little above 4. At the equivalence point 8.72, that occurred at 25 milliliters. So there's 25, and then there's 8.72. And then at 35 ml, it went all the way up to 12.22. Okay, so we only have 4 points in this titration. Okay, so we don't have a lot of points to really show you the details of the curve, but I want to kind of give you an idea of what it looks like. It essentially increases like so. Okay, so let me draw that a little bit better. So it increases and then oops, didn't mean to do that, sharply increases near the equivalence point. Okay, so the equivalence point for this particular problem occurred at a pH of 8.72. And that occurred at 25 ml. Okay, that's the equivalence point. And remind yourself, the equivalence point is where the millimoles of the acetic acid is equal to the millimoles of the sodium hydroxide, the titrant that's being added. So in a sense, what you could do is you could say the number of milliliters of acetic acid times the concentration, so I'll write this in square brackets, of acetic acid. That product is going to be the number of moles of acetic acid. That would be equal to the milliliters of sodium hydroxide that gets added times the concentration of sodium hydroxide. Those two products would be equal to each other because those two products are the number of millimoles of each of them. Okay? So there you go. So there's a nice little titration, representation of a titration of a weak acid in which a strong base is added to a weak acid. Okay?